want to figure out how we can systematically categorize the soils into groups with similar behavior. Right? So that's ultimately the objective that we're pursuing. We talked about what we mean by the mechanical behavior. For the mechanical behavior, the things that come to mind are the stiffness properties. Right? What else? Hydraulic conductivity of the soil, permanent deformation potential of the soil, moisture susceptibility of the soil. Remember, we subcategorized the moisture susceptibility into two major categories, right? Well, the main one was the shrinking and swelling potential, and the other one was freezing and thawing. So essentially what that means is that we want to make sure that the volumetric stability of the soil is maintained. Right? So shrinking and swelling means that it basically expands and shrinks, therefore you see the volumetric change. You want to make sure that that does not happen. We had an example, if you recall, when we talked about the issues with retaining structure. Right? When you have a backfill right before or right behind the retaining structure, if you use material that are prone to shrinking and swelling, you basically will see the separation of the soil from the wall. And that basically defeats the whole purpose of having the wall. Right? The wall essentially is built for restricting the movement of the soil into the highway, for instance. So the soil can sustain its own weight, there is, in fact, no reason for having that retaining structure. So that's what we had in terms of the general definition. And remember, we talked about the definition of classification of soils, and that was, remember, these are the systematic approaches that we have that gives you the most probable engineering behavior, right? And the operating phrase was most probable, right? Meaning that this is not the end objective. That means is that this is the first step. And for that, what do we have to do? Remember the components that we have to figure out in terms of the particle. Remember, we're talking about the particle sizes and we're talking about the surface properties of the fine-grained soils. For that, we have to run the sieve analysis, right? Once you run the sieve analysis, what can you get from it? Gradation parameters, right? Remember the gradation parameters, the C sub C and C sub U. Those were the two parameters that we were interested in. And today we're going to talk about the simultaneous constraint that you have to satisfy to be able to classify your soil as well-graded or poorly graded. Right? We had the definitions before. Up until this point, we talked about the shape of the gradation distributions. We talked about we were interested in elongated S-curve because it has small, intermediate, larger particles. You can fit more material per unit volume. You can maximize the density, therefore you have better stiffness properties, right? On the other hand, for the case of fine-grained material, we don't look at grain size distribution. We have a way to be able to determine that. Remember we talked about the hydrometer test, right? Hydrometer test was essentially associated with the fine portion of the mix, but typically we are not interested in the hydrometer test for classification of the fine portion of the mix because the behavior of the material does not come from the particle size, it comes from the surface properties. Right? Surface properties, in a little bit more engineering or scientific way, it would be the mineralogy of the aggregates, right? Mineralogy of the particles. And once you know what the mineralogy of the particles are, now you can characterize the moisture absorption capacity of the material. How do we do it? With simple and simplistic ways in the lab. We do it with liquid limit test, plastic limit test, shrinkage limit test, right? We call those Atterberg limits, right? And once you know what the Atterberg limits are, you can find the difference between the liquid limit and plastic limit, and that gives you the plasticity index. Where did I use the plasticity index? In the plasticity chart. Right? So in the plasticity chart, we had on the y-axis, we had the PI value, and on the x-axis, we had the liquid limit of the material. Right? So that's where we use that. And what would be the next step? You figure out what the liquid limit is, what the PI value is, and find the location on the plasticity chart. Once you know where the location is, now you have to look at the relevance of that location to 3 lines. What are the 3 lines that we had on the plasticity chart? A line, B line, and U line, right? So if in your exam I ask you what's the significance of the A line, what would you say? Clays, right? So A line essentially separates silt and clay material. Remember, silt and clays are particle sizes. Now I have the plasticity chart that can separate them from one another. Right? Not with seals, not with hydrometer, but based on their surface properties. The moisture absorption capacity. All right, we have B line. What is B line? That's a liquid limit equals to 50 line. Essentially separates the material with high plasticity, which falls on the right-hand side of that plot. Right? Liquid limit greater than 50 and liquid limit smaller than 50, that basically would be highly plastic material and material with low plasticity. And that's the reason that we show that with H and L, right? H for high plasticity, L for low plasticity. And what are the other designations that we have? Remember, for gravel, we show them with G. G for gravel. S for sand. How do we show silt? We show that with M. We don't show it with S because S is already taken for sand. So why is it with N? Meniscus is the intersection between the water and aggregate. It's the curved section between the water and aggregate. We'll talk about that. But probably the meniscus is different. All right. N stands for Niala, and that's the Swedish word for silt. And the person who developed this, Professor Kasta Grande, he was originally from Sweden. So he imported a word and everybody used it. The reason that I mentioned this is that unfortunately there is a common mistake in industry, and they say N is for mud. Mud, what is mud? It's fine-grained material and water, right? What are these? These are particle sizes. These are entirely different concepts, right? So N is for the Swedish word for silt, and ultimately we have C for clays, right? So it's very simple and straightforward when you think about that. In terms of, again, the other designations that we have, for well-graded material, that would be W for well. And we have poorly graded material, I will show that with P. So all of these are very intuitive. You know what the words are, and you can basically see the combination of the two. For instance, if I have G and W, the first one relates to particle size, and the second one relates to the gradation, right? The gradation distribution that we have. So what does that mean? You have well-graded gravel. W for well, G for gravel, well-graded gravel. So if someone in industry tells you that, I want to design the foundation of this building, go get me some GW material, now you know what that means, right? So that's basically the material that is going to be excellent for the road bearing beam. We already talked about it. The elongated S-curve and all the interactions between the particles, interlocking effect, frictional forces, and everything that is under that category. All right, what if we have CL? What is CL? C, the first one is particle size. C was for clays, and L was related to low plasticity, right? So you have CL, that would be clay with low plasticity. How about MH? What was M for? M was for silt, and H was for high plasticity. How about SP? S was for sand, P was poorly graded, and that would be an SP. And if you are responsible for designing drainage layers, you probably will prescribe SP material, right? Because that basically will create big huge gaps that allow for the moisture transference in the medium. So that's basically what it means in terms of the general engineering behavior. So we essentially designated with 2-letter, or sometimes 3 letters, as we talk about later. And that essentially communicates the engineering need. Instead of going and talking about, I need a material with extremely low plasticity and with low amounts of fines in it. I want to make sure that the gradation distribution is elongated. I want to make sure that I have very good interaction between the particles. I want to make sure there is good friction between the particles. Instead of saying all of those, we say, go get me some GW. Right? So that would be the language that engineers will communicate in the field. Right? Or if you see in a designation that they say that you are limited with the usage of CH material, that basically means that you definitely have to make sure that you're not putting material that are extremely fine and have high plasticity material in your soil layer because of all the engineering properties that we talked about. It's going to be prone to shrinking, swelling, freezing, thawing, doesn't have much of a good stiffness properties and anything associated with it. So these are very simple and straightforward way to talk about the soils. Alright, so what we're going to do today is that with that background, we're going to move quickly towards our slides, and we're going to talk about the conventions. We have 2 different ways, or let's call it 3 different ways, for classifying the soils, but the ones that we are mainly concerned about, or the ones that we focus on, would be Unified Soil Classification System. We showed that with USCS, and the other one is ASHTO, American Association of the State Highway Officials. The ASHTO Soil Classification System. So for us, in geotechnical engineering and civil engineering, for anything related to the construction work, we use these 2, probably 95% of the time with the USCS designation. Unless you're specifically in the pavement work and in the runway work, most of the time use the ASHTO designations. But other than that, these 2 are going to be the most important ones. We do have the USDA, U.S. Department of Agriculture, as the name indicates, it's for the agriculture. So the way that they designate the soils, or the way that they define the particle sizes, are very different, and also their purpose is very different from us. So I'm just going to show you how you can classify the soils according to USDA. For some reasons, in your FP test, you'll be tested on that as well. So that's the reason that I covered that in this class. Otherwise, for any other applications, you're essentially looking at the ASHTO and USCS soil classifications. And again, remember what the objective is. We want to make sure that we're using simple and straightforward parameters so we can quickly figure out what those designations are. And those simple ones are grain size distribution and information about the attribute limits. And that's all you need to be able to classify your soils. And beyond that, it's going to be running the laboratory test to get an indication of the stiffness properties, modulus properties, deformation properties, hydraulic conductivity, permeability, and things of that sort. This information doesn't give you that. It gives you a general back-of-the-envelope type of thought about the type of soil that you have. Right? So this is, in very simple terms, is the first step for identifying the soils. All right. So we start with USCS, or Unified Soil Classification System. And the genesis of that, I put together a slide that would be at the very end of the lecture so you can see how this started. So you can take a look at that one, but essentially this came in before the World War in 1944 all the way to 1948, and it was originally developed for airfield runways and highway pavements, and then later on they extrapolate that to other geotechnical applications such as dams, such as retaining structures, stability of the slopes, and foundations and things of that sort. All right, so quickly, according to the USCS, we essentially subcategorize our soils into 4 major categories. Coarse grain material, fine grain material, organic matter, and peat. Let's quickly tackle the last 2, the organic soils and peat material by definitions. Organic material, we show that with PT, as you can see in this slide. And it's essentially a sample composed primarily of vegetable tissues in various stages of decomposition and has fibrous and amorphous texture, dark brown to black color, an organic smell to it, and also it's called highly organic matter. Right? So that's basically the definition of the peat material. Hopefully you don't encounter that in the field. If you encounter it, now you have to figure out the way around it. those of you who have the stabilization class, we talked about if you have about 7% of the peat material in your soil, definitely your stabilization is going to be significantly affected by it. So sometimes in stabilization, using chemical agents are not going to be a good solution for that one as well. It has retardation effects on the hydration reactions, but that would be the subject of some other All right, the second one that we have is organic material. We show them with O for organic. Again, your organic matter could be L as low plasticity or H as high plasticity, as you can see. All right, by definition, organic is very similar to that PT that we talked about, but the way that we identify that is with our liquid limit test in the lab. You run the liquid limit test in the lab before and after oven drying, meaning that you place the material inside the oven for, say, for example, 24 hours. And since these materials are primarily consisted of roots of vegetables, roots of trees, and leaves and things of that sort, you'll see that a portion of the material essentially will burn, right? And ultimately, the difference in the liquid limit before and after oven drying is going to be more than 25% from one another. In other words, one is 75% of the other, the way that we have it in this slide. So the way that you have to identify that is based on running the liquid limit test of two samples. One, put it in the oven for 24 hours and then the liquid limit test. And the other sample is for materials that are not subjected to oven drying. If the difference is more than 25%, essentially that material will be considered as organic material. Right? So that's basically what the definitions entail with regard to this organic material. If you look at your website, I posted a paper from a good friend of mine. They're in Minnesota DOT. He's an engineer over there. And they encountered a soil of highly organic matter. And if you read that paper, they talked about 4 different solutions that they explored for building bridges and highways over that organic soil. So you can take a look at that. They looked into, obviously the first option always would be removing the soil, right? So if you have a lot of organic matter, probably the first and easy way to think about would be, let's remove the soil and replace that with good quality material. It might be a good idea if you're looking at limited space for construction, such as the foundation of this building. But what if you're designing a 20-mile highway? Can you just go in and dig in all the soil in there? You don't. You can't because of the cost issues. So on the other side, you have to look into other approaches. So essentially, they looked into short bridges and all the other ways that they can do in order to essentially build over that organic matter. So that would be a very good and very interesting paper that you can see how engineers tackle the issues of organic matter. But this is as far as we go with the organic materials. Let's talk about the major part, the major applications that we have, and that would be for the coarse-grained and fine-grained material. A lot of these materials, we already talked about those, so we can quickly move forward with the definitions and the conventions of the USCS soil classification. All right, so we have the coarse-grained material. And essentially, the stiffness of the material comes from the interparticle frictions and interlocking effect that we have. On the other side, we have the fine-grained material. And that would be the cohesive bonding between the fine portion of the mix. As far as the definitions are concerned, we have gravel and sand on the coarse side, and we have silt and clay that falls under the material that passes seed number 200, right? Remember that 75 microns or 0.075 millimeters that we talked about. Now, the distinction according to the USCS between the gravel and sand is sieve number 4 for material that are smaller than 4.75 millimeters, as you can see in that. So essentially, the sieve numbers and sieve openings that you have to remember are essentially 2 of them. Sieve 200, we already are fairly familiar with that, 75 microns. The other one is sieve number 4. And the significance of sieve number 4, according to USCS, is that it separates sandy material and organic material. Right? So these are the definitions. Later on, when we start talking about the Oster classification, you'll see the distinction between these. So it's a good idea to take note of these numbers. talking about the side-by-side comparison of the USCS and AASHTO here. The first major distinction that you can see is for the fine-grained soils, we have distinction between silt, clays, and colloids under the AASHTO classification, but we don't have any separation between the silt and clays. How do we determine that? Based on the attribute limit test and the location on the plasticity chart, right? But for this one, for AASHTO, you actually have size limitations. Between 75 microns to 2 microns, we call them silt. Between 2 micron and 1 micron, we call them clays. And anything smaller than that, we call them colloids, right? So that's basically the definitions that we have here. Notice that the bands and the ranges are also a little bit different from one another, right? On the far end side, as you can see, they're relatively the same. That would be the distinction between the cobbles and boulders. Would be 75, would be the same, 300, 305. Again, these values are in millimeters, and they're relatively the same. But notice that the ranges for gravel is much larger, for the sand is more compressed. When you're looking at the comparisons of USCS and AASHTO classifications. Later on, when we talk about the AASHTO, we'll see that we talk about this AASHTO classification was originally developed for highway pavements, and we want to limit the amount of fines for highway pavements. And you see that's